So far, we've introduced ANOVA as a method for comparing many means to each other concurrently. Finding a statistically significant result at the end of an ANOVA, however, only tells us that at least one pair of means are different, but not which pair of means are different. In this video, we set out to answer this follow-up question. And when doing so, we're going to discuss how to control the type 1 error rate that would be inflated by doing many pairwise tests in the quest for identifying groups whose means are significantly different from each other. Remember that to determine whether two means are different from each other, we use t-tests. And with each test that you do, you incur a probability of doing a type 1 error. The probability of committing a type 1 error is the significance level of the test, which is often set to 5%. So when you do multiple tests, you're going to be inflating your type 1 error rate, which is an undesirable outcome. Thankfully, there's a simple solution. Use a modified significance level that is lower than the original significance level for these pairwise tests so that the overall type 1 error rate for the series of tests you have to do can still be held at the original low rate. Testing many pairs of groups is often called multiple comparisons, and a common modification that we use when doing multiple comparisons is the Bonferroni correction, which uses a more stringent significance level for each of the pairwise tests. More specifically, we adjust our alpha by dividing it by the number of comparisons being considered. For example, if you have 4 groups in your ANOVA and it does yield a significant result, then you need to compare group 1 to group 2, 2 to 3, 3 to 4, so on and so forth. But counting these out is somewhat tedious and error-prone, so we usually use a shortcut formula for determining this value and then use this value to adjust the significance level. So the Bonferroni correction is a two-step process. First, find the number of comparisons as k times k minus 1 divided by 2, and then correct your original alpha by this level as alpha divided by the number of comparisons. Let's practice this. The social class variable we have been considering has 4 levels, that is k equals 4, and if the original alpha was 0.05, what is going to be the modified significance level for the multiple comparisons tests? Each group needs to be compared to 3 other groups, resulting in a total of 12 comparisons. But if you've already compared group 1 to group 2, say middle class to lower class, you don't need to go back around and compare lower to middle again. So the total number of comparisons can be cut in half. Hence the formula k times k minus 1 over 2, which results in 6 total comparisons. And we can use this number to correct our significance level down to 0.0083. This is the significance level we're going to use for the pairwise comparisons to see if 2 pairs of means are different from each other. There are a couple other considerations when doing these multiple comparisons after ANOVA. First is related to the constant variance condition. Since for ANOVA, we need to meet this condition, we need to now rethink the standard error and the degrees of freedom to be used in the multiple comparisons tests. And of course, now we have a new modified significance level that we're going to compare to the p-values of these tests to determine significance. So what are these consistent standard error and degrees of freedoms we need to use? The formula for the standard error should seem familiar to you, except that instead of the individual group variances, we're actually using mean squared error from the ANOVA table. Remember, the mean squared error is actually the average within group variance, so we're still getting at the same thing, the individual group variances, but now we have a consistent measure that we can use for all of the tests. If indeed the constant variance condition is satisfied, this value should be very close to your group variances anyway. And the consistent degrees of freedom is going to be the DF error from the ANOVA output, as opposed to the minimum of the sample sizes minus 1 from the 2 groups that we're comparing. So let's put all of this information together, pick one of the pairs of groups, and do the comparison. Is there a significant difference between the average vocabulary scores between middle and lower class Americans? Our hypotheses are, in the null hypothesis, there is no difference. The averages are equal, and the averages are different for the alternative hypothesis. we calculate our t-score as the difference between the two group means minus 0, our null value, divided by the standard error, calculating the mean square error from the ANOVA output. That is 6.76 for the average middle class score minus 5.07 for the lower class score divided by the mean square error, which yields a point estimate of 1.69 and a standard error of 0.315 for an overall t-score of 5.365. And the degrees of freedom comes from the ANOVA table, 791. Let's clean up our plate here, write down our test statistic and the degrees of freedom. And before we can finally get to the p-value, remember to always draw the curve. So here's our t-distribution with 791 degrees of freedom, which, by the way, remember, is going to be just like the normal distribution at this point because of the really high degrees of freedom. And a t-score that's so high, that's 5 standard deviations away from the center, is going to result in a really tiny tail area because it's really unusual to get an observation that's more than 5 standard deviations from the mean. It's also clear from the sketch with the really skinny tail areas when you get that far from the center. We can also use R for this. We use the PT function, and remember to multiply one of your tail areas by 2 to account for the two-sided alternative hypothesis. And also remember that the significance level we're going to use for this test is that modified significance level we calculated earlier. So even though that was very conservative and stringent, because we have a pretty tiny p-value, we actually can reject the null hypothesis again.